Today, we are gathered here for the much-awaited webinar on topic Changing Faces of Optical Communication. Today's society relies on fast and reliable exchange of information. Advanced communication systems support the operation of industries, businesses, and everything you can possibly think about. So to know more about optical communications system and its evolution over the years, I welcome you all to today's webinar. All queries regarding the webinar are welcome. Feel free to put your questions in the chat box. It will be answered at the end of the session. Now let's welcome our keynote speaker, the very honored Dr. Deepa Venkatesh ma'am. She's currently professor at Department of Electrical Engineering, IIT Madras. She has received the Young Faculty Recognition Award, IIT Madras, and is also a recipient of the Abdul Kalam Technology Innovation Fellowship of INAE. She is also a senior member of OSA. Her research interests include optical communication, high spectral efficiency communication systems, optical signal processing for high-speed systems, fiber lasers, non-linearity mitigation in high-power lasers, and fiber sensors. She is also the Associate Editor of Advances in Optics and Photonics, Editorial Board Member of Photonics Network Communications, and Associate Vice President of Women in Photonics.
Shall I start?
Hello, everyone. Hi, ma'am.
Yeah.
Good evening, everyone. A warm welcome to everyone present here. Today, we are gathered here for the much-awaited webinar on topic Changing Faces of Optical Communication. Today's society relies on fast and reliable exchange of information, which is supported by advanced communication systems. So to know more about optical communication systems and its evolution over the years, I welcome you all to today's webinar. All queries regarding the webinar are welcome. Feel free to put your questions in the chat box. Now let's welcome our keynote speaker, the very honored Dr. Deepa Venkatesh ma'am. She's currently professor at Department of Electrical Engineering, IIT Madras. She's received the Young Faculty Recognition Award, IIT Madras, and is also a recipient of the Abdul Kalam Technology Innovation Fellowship of INAE. She's also a senior member of OSA. Ma'am, I'm sorry about repeating it. I thought you didn't hear it the first time. I thought I was inaudible.
I could hear it very well.
Okay. I thought there was some glitch when you asked again if you could. I'm so sorry about the
there was a gap.
confusion.
I said, should I start? That's what I was asking.
Yeah.
Shall I just go ahead and start?
Yes, ma'am.
It's quite boring to keep listening to the same thing again. Can you see my screen?
Yes, ma'am.
Is it full screen for you?
Yes. Yes, ma'am. Screen is visible.
Okay. Thank you very much to the officers of IEEE Photonic Society Kerala chapter. Are you able to hear me?
Yes, madam. Yes, we can hear you.
Now I'm nervous that Suresh sir is here now. Today's talk is just to give you it's nothing to do with the details of the work that we do in our lab, but just to give you a glimpse of the changing phases of optical communication. When I say phase, it actually means phase as an era and also phase as in phase in electromagnetics. So we keep using these changing phases, and I'll tell you how we are using this. So there are very senior people here. If it's too elementary, you can stop me. I can keep going further. So this is the outline. Please feel free to interrupt anytime. Let it be a discussion rather than monologue. Why fiber optics? Just to kind of keep everyone up to speed if there are people who are not familiar with fiber optics. just give you a glimpse of the evolution of technology from, intensity modulation, direct detection systems, which is kind of obsolete now, and moving on to coherent systems. We'll talk a little bit of what is coherent in a coherent system. We will talk about a little bit of what we have at IIT Madras without giving too much details. Then we jump gear and we see why do we need to increase the capacity or data rate, because fiber has infinite bandwidth actually. And how can we do that, and what are the multi-pronged approaches industry as well as academic research is doing to help in increasing the capacity. So fiber optic communication is actually ubiquitous. Even though you may be making a cellular phone call from here to your friend or family in a different continent, the information is in the air only for a very, very small fraction of its transfer. The majority of time, the information goes into your tower. It gets linked into a metro network. It may get linked into a core network where it can go through a submarine transport. It may even get linked to a satellite network and come back and get back to the access metro cellular networks of your receiver. More importantly, the fiber optic communication has become really essential in data center networks. The huge amounts of data that we are accessing, downloading, uploading in data centers, in clouds, the servers are connected through optical fibers. Radar systems is one network which is probably not directly using fiber optic communication links, but they've also started using fiber optic links in the analog domain to make them more agile and more multifunctional. So why use optical fibers at all? Why can you not use copper cables? This is a textbook material. We know that this is the attenuation, the loss in decibels per kilometer for different types of transporting medium. If it is a copper cable, first thing you notice is that it works for specific frequency range. The x-axis actually shows the frequency range. Works for specific frequency range, which means that if you're trying to transport a different frequency, you will have to change the type of cable. Whereas an optical fiber, if you see, the attenuation is constant. So this is one unique reason. Even radar systems, analog systems are trying to move on to fiber so that they don't really have to change the transport cable when their frequency changes. Now, just to trace the history, it all apparently began with Indian by name Kapani, who was working on a project with Hopkins, and they were trying to develop a fiber scope, which is an endoscope. And through just static scanning, you just put multiple fibers. Everyone knows what an endoscope does. But even though he had nothing to do with communication, this work actually established that light can be guided through bending by bending glass, and this is turning out to be the origin of the whole evolution of optical fiber. So he's still called as father of fiber optics. Of course, things changed and it became useful, viable for communication when Charlie Kao did demonstrate, and his group demonstrated 4 dB per kilometer attenuation in 1970. And what is, this is a paper from NTT in 1979. You see from 1970 with an attenuation of 4 dB per kilometer, what NTT developed is, demonstrated is in 1979 is ultimate low loss, and this is 0.2 dB per kilometer. And since then, believe me, the progress has been very incremental because what is fundamentally achievable from glass was already achieved at that time. Today's state of the art telecom fiber is something like 0.17 dB per, the best fiber is 1.17 dB per kilometer. So that's what is currently used in all the communication systems. Now, to trace the history of how things evolved, it all evolved by a simple non-return to zero signaling. You just, so all that communication that happens today, majority of optical communication is digital communication, which means you have binary data, zeros and ones, which needs to be transported to a distance. So these zeros and ones, how do you transport it? The simplest way is you turn your light on and off, right? You just have a switch, turn it on and off. That is called as on-off keying, or OOK modulation scheme. So you turn the transmitter on and off. You have a receiver, which basically is a photodiode. It's a direct detection receiver, which means that as soon as it receives a signal, it just sends a photocurrent. That current gets converted into voltage, and the voltage levels is thresholded, and that is how communication happened, right? So this is a simple intensity modulation direct detection system. Was commercial even as early as 1975. Not many systems, but for few systems. You look at it in the constellation space. This constellation space is nothing but Argand diagram. On the x-axis, you show the real value, y-axis, you show the imaginary component, right? There's no imaginary component because it's just 0 and 1. So the signals would either occupy this space. I don't know, is my pointer visible to you?
Yes, madam. Yes.
Okay. So the signal is either found in this 0 or it is found here. So this is the constellation space that we are talking about. It can take only 2 points in the constellation space, a 1 and a 0. It's along the real axis because you are just making the intensity low and high. There's nothing complex or there's no phase in this way of information transfer. Of course, you can directly turn the light on and off, but that poses a certain limitations on how fast you can turn the light on and off. So instead of direct modulation, the next generation of systems started using what is called as external modulation. And I had the great opportunity to work with Dr. Nair here as a project scientist in developing one of the early external modulators in India. The data rates we had targeted was 2.5 gigabits per second. So we were in the business of making this Mach-Zehnder interferometer based external modulator. There are several advantages of doing external modulation when compared to direct modulation. The first thing is the speed. Other things, let's just forget about it. And students who have to do a course can do the details. But the detection remains the same. It is a direct detection receiver, right? We do have Mach-Zehnder modulators way back in 1997, 98. We were working at 2.5 gigabits per second modulator. The state-of-the-art modulator today is 96 gigabits per second, or 96 gigabaud signaling is the state of the art that I can buy today, right? So that is how the technology has progressed, in the last 15 years or so, or more than almost 20 years or so. So moving on, 1980s, that is the era where people started using heterodyne detection. So what was the problem here? We wanted to transport the data for longer and longer distances. So this one started getting closer and closer to 0. So distinguishing 1 and 0 becomes a problem. So the sensitivity of the detector had to be improved. You wanted to have detectors which could sense very small change in the power level. So people thought of using something similar in radio systems. Radios always use a local oscillator and a heterodyne detection. Here, the local oscillator and the heterodyne detection along with balanced receivers were used to improve the sensitivity. You can go all the way up to short noise limited sensitivity, which is a quantum limited sensitivity. So if there is a question, I can talk about what is quantum about this sensitivity, but then we will respect quantum and say that this is the best sensitivity that you can achieve. And this helped the photodetectors to detect very, very small voltages, very, very small optical powers. So what's the benefit of doing that? You could increase the transmission distance a little bit more further. But the whole scene changed when EDFAs came into picture. EDFAs are the erbium doped fiber amplifiers, I sometimes wonder why EDFA didn't get a Nobel Prize as yet, because this has really changed the commercials of how optical communication happens. So you don't need any more coherent detection or the heterodyne detection. Instead, what you could do was, if the signal was weak, you can amplify it in the optical domain itself to get a stronger signal. But the way I have intentionally drawn these wigglies is such that, you see, in addition to getting amplified, the noise also increases, because after all, EDFA is a amplifier where there is spontaneous emission in addition to stimulated emission that happens. So there is some noise that gets added, but you don't care about the noise so long as the SNR is good enough. So these amplifiers actually revolutionized the way the fiber optic communication technology progressed, not only because it could amplify, but also because it could amplify multiple colors simultaneously. EDFA had a large wavelength band, large color band, it could amplify simultaneously. So what happened was, you can imagine that just like in a highway, you have multiple lanes, you can use the same fiber, you can use the same amplifier, but have multiple paths, multiple lanes, or multiple colors on which you could modulate, transport, you add drop wavelengths wherever you want, and then the capacity of the fiber dramatically increased with this technology of wavelength division multiplexing. This was done and dusted in 1995. Okay. So this was the state of the art around that time, that 80 DWDM, dense wavelength division multiplexing channels. These are, highways, these are the lanes of the highway, which is marked at 50 gigahertz. Each lane was modulated at 10 gigabits per second, which was considered to be really high, which could be direct modulated or external modulated, depending on how far you want to go. So you could actually transport 0.8 terabits per second, 80 multiplied by 50 gigahertz in 4 terahertz of spectrum. So people did not pay attention at that time, but the number was that it's a question of how efficiently are you using the spectrum, right? So you're actually transporting in 0.8 terabits per second in 4 terahertz of spectrum. So your spectral efficiency, which is number of bits divided by bandwidth, that is 0.2 bits per second per hertz, which means in 1 hertz of frequency, you are transporting only 0.2 bits per second of information. Why is this number important? I'll tell you later. That number became important because EDFA could amplify only this much, but our demand for capacity started increasing. We started requiring more and more data. After 1995, there was a lull, there was a, big, negative economic slowdown in the commercial fiber optic industry around this time, because this was a lot of data. But after 2000 or so, that's when internet became very common, mobile phones became very common. And again, we started seeing an increased demand for data rates that could be transported through optical fiber. And so this 0.8 terabits per second, I will show you later that this 0.8 terabits per second is something that is required between any cell phone tower to the base station today, right? Whereas this is all what you could carry across the submarine at that time. So how do you now make sure that you don't change the fiber, you don't change the amplifier, but still increase the data rates? That is when you got into this whole research of increasing spectral efficiency. And I'll tell you an open secret, there is no new innovation here. It is only borrowing concepts from wireless communication technology. But the challenge is technologically, how do you implement it in the optical carrier frequency, right? So the ideas were all there in the wireless communication systems, but how do you now overcome the technological challenges of introducing or inducing them in the, implementing them in the optical communication system? So for those of you who are from the physics background, I can tell you, give you a very short primer of how phase starts becoming important, or how this modulation formats change, how we get into this whole world of what are called as advanced modulation formats, where we completely go away from intensity modulation, direct detection, on-off keying, and you do something what is called as QPSK, quadrature phase shift keying, or 16 quadrature amplitude modulation, and so on. Essentially, what you're doing is you're increasing the number of points in your constellation space. Now, what is our idea? In your original binary stream, you would transport 0 and 1 in a regular OK system. Now, in this QPSK, what you're trying to do is, instead of sending one bit at a time, why don't we group 2 bits together and call it as a symbol? So if I take 2 bits together, I can have only 4 combinations, right, in a sequence. It could be either 0, 0, or it could be 0, 1, or it could be 1, 0, or it could be 1, 1. Now let me call this 0, 0 as symbol A, 0, 1 as symbol B, 1, 0 as symbol C, and 1, 1 as symbol D. Now instead of transporting a 0 and a 1, what I will transport is ABCD. Okay, so first I do this mapping from binary stream to this coding, which is where 2 bit is encoded into what is called as one symbol with 2 bits per symbol. And I need to figure out a way to transport 4 distinguishable points in the constellation space. Now, what could be those 4 points? It could be 4 points like this, or it could be 4 points like this. So let's say now I imagine that my constellation space, remember in OK it was 2 points. Now I say that I'm trying to transport one among the 4 points at a time, which means if it is a 0, 0, I encode a phase of 45 degree in my optical carrier and transport it. If I happen to see a 1, 0, 1, 0 is somewhere here. So I encode a phase of 135 degree, right? And minus 45 degree, and 90 plus 45, this is 135, this is 135 plus 45, and so on. So there are 4 phase levels that we want to encode, right? How do I do that? I use what is called as an IQ modulator, in-phase quadrature modulator. So the first bit goes into a 0 or a 1, or minus 1 or a plus 1. The second one goes to minus 1 or a plus 1. I do a phase shift of 90 degree in the second modulator. So this is basically a nested modulator. And all possible combinations of these 4 constellation points will give me 4 distinguishable constellation points. And I basically rotate it so that they can be identified in a specific quadrant, right? So all what I need to do is to do a phase modulation in one arm, another phase modulation in the other arm, and then do a 90 degree phase shift on the second arm so that it becomes a quadrature modulation and transport. So in this QPSK, you have 1 level of amplitude, 4 levels of phase, 4 points in the constellation. You are encoding 2 bits per symbol. This is what is the beginning of advanced modulation format. This was first, the standard was established in 2005. Okay, and with this came the era of digital signal processing. No more could you say that my intensity is a 0 or a 1. You can't do a threshold detection now. You need to have some mechanism to identify the phase of your incoming signal, which means that the laser should retain its phase, which means that you can't use an LED. The laser should be highly monochromatic. It should be coherent. Only then laser phase by itself should not change. Only then you can encode phase into the laser, right? So that is where the coherence in coherent communication is coming, the coherence of the laser, right? Because you have started using phase as one degree of freedom, okay? Now, so how do you do the detection? So here now the heterodyne detection becomes a necessity. Any phase, whatever you do, the phase can be detected only through an interferometer, right? So you're basically having mini interferometers in all your receivers. So what are you interfering it with? You're interfering it with another laser called as a local oscillator laser. With your, this is your signal. It goes into this chain of couplers with a 90 degree hybrid. You basically work out the math. It will turn out that one set of balanced receivers will give you the in-phase component, the x-axis, the projection of this data on the x-axis. The other detector will give you the quadrature component. So once you know what is the in-phase and quadrature component, you can basically identify your symbol. Once you identify the symbol, you can get back to your bit stream. So this is the idea of advanced modulation formats. And today's commercial high-speed communication, 100 gigabits per second high-speed communication, that's a standard today that runs on quadrature phase shift keying. You signal at 25 gigabaud, which means you don't have to signal fast. You have to just signal only at 25 gigabaud, but you can transport 50 gigabits per second. So because the signaling is done only this slow, what you can think of is that the occupied spectrum remains the same, but the bit rate increased. So your spectral efficiency increased. Okay. Now, in addition, you can also, because light is an electromagnetic wave has to, can be always decomposed into two unique polarizations. You can always multiplex the data in two polarizations. So today's 100 gigabits per second standard, which is commercially available, runs on this engine, which is 25 gigabaud, signaling with QPSK, so 2 bits per symbol and 2 polarizations. So that is 100 gigabits per second. So you have PM or PDM or polarization division multiplexed QPSK that runs as the standard today. Now, we don't have to stop at 4 constellation points. You can keep increasing the number of constellation points. What if instead of 4, I pair, instead of 2 bits, I pair the 4 bits at a time and create my symbol accordingly. Here, what is the advantage? Instead of 2 bits, now in one symbol is represented by 4 bits. So because you have 4 bits, which is representing a symbol, there are 16 combinations you need to transport, which means that you need to find out 16 unique values of amplitude and phase, modulate it that way, and do the detection. So this is a current standards for 200 gigabits per second, right? 200 gigabits per second is also standardized. The signaling is, the electronics works only at 25 gigabaud, but the data rate is at 200 gigabits per second because there are 4 bits per each symbol. So 25 into 400, and then there is 2 polarizations. So you see the spectral efficiency, where it was 0.2 bits per second per hertz. Now it has come down to, increased to 4 bits per second per hertz. What is the additional challenge? It turns out that all the fiber optics communication engineers now started opening their digital signal processing books, right? Because that was not a necessity at all earlier, but now it becomes a necessity because these are some examples of what we had data from the lab, where this is how the constellation, QPSK constellation looks like after chromatic dispersion. This is what we receive. It doesn't look anything like a constellation. You do chromatic dispersion, then there is a frequency offset between transmitter and receiver laser. After the frequency offset correction, so all these are algorithms that we are running, which are physics inspired algorithms. We know what is frequency offset, what is its consequence on constellation. So we basically do the inverse system for this impairment. Right? This is after polarization demultiplexing. This is after downsampling to 1 sample per symbol. This is after phase noise correction. This is after some timing recovery correction. After some adaptive filtering, you have recovered your constellation. So signal processing, those who are expertise now in signal processing, you need to now have signal processing expertise to do anything basic in optical communication. This part of my talk is over. I'd like to take questions from this part. I have no, there's no reason that I should finish all the slides, but if there are questions to be discussed or if you have something burning, please discuss now so that this becomes a useful session. This is not necessary at all that I finish all my slides. So are there any questions? Is there a way you can conduct some poll? Does the software allow you to conduct some poll? Binu, is that possible?
I think it is not equipped now, I think. Looks
Okay,
like.
I should have said this earlier.
Yeah. Maybe anything on chat box, I think nothing is seen, only one line is there. Yeah.
Is there a question in chat?
Students, yeah, please ask questions. Then only it will become interesting. Otherwise, this will become a monologue.
Yeah.
Around 61 people are there.
Yeah, because we keep lecturing, right? So
Yeah.
this is in the online class we keep asking questions, then we keep wanting the students to show their face and ask a question. Otherwise, we just go still. So I'm just following that what I do for my regular classes here.
I think probably you can continue and later on we come up with something.
Yeah, maybe it's all too elementary. Is that something that you people teach in the courses?
No, the attendees are all students. Some of them are, I think, MSc in photonics and
Okay.
MTech in photonics, right, Binu?
Yes, sir. Yes, sir. Yes, sir.
Okay. I think you can continue.
Okay, I'll continue. Yeah. So now we are very greedy now. We want to keep increasing the spectral efficiency. Now, how do we do that? So what we do is there are two things that can be done. If you look at the way 10 gigabits per second data got transmitted, you see in the 50 gigahertz spectrum, you're occupying only a very, very small part of the spectrum because you did NRZ modulation, the non-return to zero modulation. In the spectral domain, this everyone knows. If you have a square in the time domain, in the spectral domain, it is a sinc, right? So that sinc function, you try to accommodate as many lobes as possible. You're very lavish in utilizing the spectrum. But it turns out that the spectrum is not that lavish simply because the EDFAs are limited bandwidth. It cannot amplify a very wide bandwidth. The fiber can take a lot of wavelengths, but amplifiers cannot amplify a large number of wavelengths simultaneously. So people started thinking about why should you leave these kind of guard bands? Can we not occupy all this spectrum? That gave rise to this idea of Nyquist pulse shaping. Nyquist pulse shaping. Nyquist is the limit to that pulse shaping. So what you can do is, this is the regular spectrum. You can apply a function, a cosine square or a cosine function, a transfer function in the time domain. So instead of doing a square, what you do is you apply a sinc in the time domain. What will happen in the Fourier transform will become square. So what was a sinc in the frequency domain, because of the square in the time domain, you basically make it ulta. In the time domain, you make it sinc, so that in the frequency domain it becomes square. Why do you want to make it square in the frequency domain? So that it becomes compact. It occupies small spectrum. So this is an example where the spectrum is shaped by doing this time domain shaping. So the spectral occupancy is reduced. So this is a result actually from the experimental result from the lab actually. What we have is lambda 1, lambda 2, lambda 3, lambda 4, or lambda 1 to 5. There are 5 comb lines which we generated, frequency combs from a single laser. You do some tricks with the modulator. You generate these 5 lines. Each of these lines can be now modulated with this kind of square, right? This square which fills up to half of the spacing, right? The second line also gets modulated this way. Third line is also. So the modulated spectrum is what what I'm showing in blue. You can't distinguish because there's no guard band here, right? And this, what is the benefit? Now, this is called as a super channel now. Why is it called super channel? It is called super because it is kind of packing a lot of information within the available bandwidth, which means earlier within 100 gigahertz, you had 2 10 Gbps. Now what we are saying is in 100 gigahertz, you can actually have 5 channels and you don't have to leave any guard band. Increase the spectral efficiency. These are experimental spectra from the lab. You can't basically distinguish these at all. What is it that we are losing? It requires a lot of additional signal processing to recover this data. Here is how the transceiver looks like. Maybe I can show you this picture, or maybe this is a picture where a commercial transceiver, this is how it looks like. you have the digital data, you have to do some kind of processing and then feed it to the digital to analog converter, goes into the IQ modulator where you do this in-phase quadrature modulation. Then you need to do the same thing for the Y polarization. So you basically replicate transmitter in the Y polarization, combine it in a polarization beam combiner. This becomes a part of the transmitter. Now in the receiver, what do you have? There is a polarization beam splitter, there is a data, then there is a local oscillator, which is also split into two polarizations. There is a 90-degree hybrid, which will isolate the in-phase and quadrature components in polarization. Output goes into an ADC, you digitize, it's a 4-channel ADC, you digitize the output, that digital data you do signal processing live, and then you recover it. Of course, in the lab, we have a noise injection to emulate the real system. To give you a perspective, this is how the coherent transceiver, which contains all these components, this is how it looks like. If you see the dimension, it is 10 centimeter by 4 centimeter by 1 centimeter. That's how packed the whole thing can be by photonic integration. So a lot of expertise in device fabrication, in signal processing, combining the electronics with optics, all that goes in building this kind of transceiver. Of course, this is from Lumentum. I have, it's not that Lumentum is my favorite, but it's just first thing that came across in the Google search. You see, these transceivers now, it's important to understand what they're capable of. They could do 100 gigabit, 200 gigabit, 400 gigabit Ethernet. They could do non-return to zero, 56 gigabaud PAM4, which means the signaling can go all the way up to 56 gigabaud, not really 28. They could support 100, 200, 300, 400 gigabits, QPSK, 16 QAM, all kinds of modulation formats, up to 66 gigabaud actually, not even 56. Now, they all seem to be using Nyquist spectral shaping, what I talked about earlier, and all the electronically compensation for chromatic dispersion, the digital signal processing for all these compensation. It is flexi-grid deep blur WDM, which means that the laser can keep moving its wavelength. It's not coming as a fixed grid. And of course, there are other standards which are complying to the IEEE standards and so on. This is, of course, the photograph of the setup from our lab, where you have a transmitter, then this is the noise loading stage, and this is the receiver, and this is where the computer where all the processing happens. This is a photograph while an experiment was happening, where you can see the 16 QAM constellation on the X polarization and Y polarization. Moving on, where is the technology going? So fixed grid, DWDM grid, where channel numbers were specified, that era is going. Instead, people are moving to elastic grids, meaning different operators are not really working with specific grids. They actually now work with a group of grids, so that depending on the traffic, they can either choose OK, or they could choose QPSK, or they could choose what is called as a super channel. I showed you 100 gigahertz example. This is an example where 150 gigahertz is used to demonstrate 400 gig super channel. So this is the standard, one of the standards for demonstrating 400 gigabits per second. They take 150 gigahertz. They have basically 4 carriers, and in each carrier they have 37.5 gigahertz of data. Right? So it becomes important to have optical frequency combs. Right? Optical frequency combs are nothing but sources which can give you multiple lines which are correlated. You don't want the phase noise of each of them to be very different, so you want correlated source. So which is why you don't want to use independent lasers, and you use Nyquist shaping and to pack your spectrum. So this is again an example from our lab where we have demonstrated 1 terabits per second with optical frequency comb. So this basically has 32 gigabaud electronics, polarization multiplex 16 QAM. We took 4 comb sources, 4 comb lines. In fact, in this experiment, there is a small guard band also left for ease of signal processing. And the error vector magnitude is way less than what is better than what is allowed by the standard error correction algorithms allow. So this is just to say that we can keep scaling the technology by increasing the modulation, by adding frequency combs, and so on. But the thing is, do we really need this high capacity? 1 terabit per second, is that really necessary? So I'm not going to show these specific numbers. This basically tells you that the internet speeds are increasing. The number of fiber kilometers per capita is really high. But what I would like to bring to your attention is that the success of 5G or 6G or 7G or whatever G in the wireless communication, that depends on high-speed optical capacity, high-speed optical communication links. Why is that so? You see, as you increase the, what's the difference between 2G, 3G, 4G, 5G, etc., the carrier frequencies change, right? So the antennas become highly directional, which means you may need more number of antennas to cover the same areas. So in a 3-sector antenna, it will be like a triangular structure. Each will be a phased array antenna, and each antenna will cover 120-degree kind of direction, azimuthal direction. Now you need to feed in data for each of these antennas, and the bandwidth, all these Gs, as the Gs increase, the data rate is increasing, which means that the bandwidth carried by the cellular signal increases, which means that there must be somebody who's actually carrying that information all the way up to the antenna. Earlier, the antennas and the base stations were all in the tower. But now what has happened is that there is a split there. There is a remote radio head, which is the antenna, which is basically the power amplifier, which is feeding the antenna. Then there is this baseband pool, which is all aggregated because number of antennas became really large. So the computing resource was actually at a central location. It is more like a cloud, access network, radio access network. So the processing as to which signal should go to which antenna, how should the beamforming happen, all that happens in a BBU pool, which services multiple antennas. And these antennas could be located anywhere between 100 meters to 1 kilometer. And so there is a fiber optic network that runs between the baseband processing pool to this front, to these antennas. And it turns out that if you do the calculation according to the radio standards, this front haul network may even require, today, even in this LTE, it is requiring 25 gigabits per second, this small network. If you further advance to advanced MIMO system for 5G and all, you can even need terabits per second data rates in this front haul network, right? And of course, there is backhaul, where we talked about how these cellular networks get connected to the core network and so on, optical network. That is all done in the backhaul. That anyway is fiber is required. But as the wireless technology progresses, what we are seeing is increase in the data rate in the front haul network. And where is this front haul network? It is between every tower that you see and a baseband pool, as I said, between 100 meters to about a kilometer. This is again an illustration of the same thing. So this is the 3-sector antenna that I was talking about. Turns out that if you do the calculation for 200 megahertz 5G signals in this 3-sector, from the baseband unit to this antenna, if it is a 5G antenna, you need 2.4 terabits per second, right? Now, how do you do 2.4 terabits per second? You can do 100 gigabits per second and put in 240 pieces of fiber, or you can do something smarter, right? So again, let's skip this, where the that's more of commercial, maybe of not of interest to you. So terabits per second data is actually required. Okay, I just distracted with the chat thing happening. Okay, so terabits per second is, oops, why is this? Yeah. So we are convinced that we need terabits per second in the very, very near future. It's not like in 10 years we need it, right? What actually limits us from scaling? Can we not increase 64 QAM to 1024 QAM or 2048 QAM, or what is the fundamental limit there? So this fundamental limit was our good old Shannon's capacity theorem, right, where he predicted that for any linear channel, right, which is white noise, additive white noise, Gaussian white noise limited channel, as you increase the constellations, essentially the y-axis is the spectral efficiency. I told you how to calculate the spectral efficiency. This is the required signal to noise ratio. Here is the line that shows the limit, which means if you have a 10 SNR of 10 dB per bit, you can transport only this up to this. So 3, 4, 5, about 6 bits per second per hertz. That's the fundamental limit. On the other hand, if you have 20 dB SNR, you can transport up to even 10 bits per second per. So this limit is already decided. Now, how do you scale from 1 bit to 10 bit? I already told you, you can increase the number of constellations to scale the spectral efficiency from 1 bits per second per hertz to 10 bits per second per any number of constellations. So the bottom line is, if you're increasing the number of constellations, the SNR required to reach the same spectral efficiency goes on increasing, which is actually logically understandable, because if you want to decipher 16 points or 256 points, the phase noise and the amplitude noise tolerance, the constellation becomes closer and closer. So it needs more and more signal to better and better signal to noise ratio. Noise should be smaller so that you can identify all these constellation points. But the problem people are working on is, here is the Shannon limit, and these dots are actually telling you the state of the art demonstrations. And there is a gap. There is a gap here, right? So practical systems are not yet reaching this Shannon limit, right? So there is a group of people who are trying to attempt, how do I now, this is only engineering which will, there is no fundamental limitation. It is only engineering that will help you to reach from, for example, this SNR is only here, but it can ideally reach up to this spectral efficiency. Why is the SNR degrading in an optical communication network? As you increase the number of spans, one span is typically 80 kilometers. So as you increase more and more, increase the distance, you will keep putting amplifiers. And as I remember, I told you that amplifiers keep adding noise. So as you keep on increasing the number of fiber spans, you're adding more and more amplifiers. So the noise degrades. So the optical signal to noise ratio actually falls as you increase the number of spans. So if you're going long distance, the signal to noise ratio is going to be poor. And if the signal to noise ratio is poor, you cannot do 1024 QAM, you have to come back to QPSK, right? So these are the multi-dimensional challenges here. But even with all kinds of fancy error correction codes in information theory, we are not reaching the Shannon limit. So this is the four-pronged approach, and people who are interested to do research, these are one of the 4 areas you need to pick. If you were to do research in the area of hardcore fiber optic communication technology, as to how to approach the Shannon limit and how to go beyond, can we dare to think going beyond Shannon limit, right? The four-pronged approach are the following. One is, you can try approaching the limit. For that, it is only smart choices for modulation. You have to keep inventing, reinventing to find out that nice modulation scheme, find out nice pulse shaping schemes. I'll show you a couple of examples so that you are able to reach the Shannon limit. The second is, you don't try to beat Shannon. It has nothing to do with Shannon limit. You approach the problem differently. You ask yourself the question, what is fundamentally limiting you to increase? It's the EDFA. So don't use EDFA. Use something else for amplification, right? Expand the carrier frequency. You use what is called as ultra wideband, right? Take EDFA out of the picture. Put another amplifier or put another amplification system which is able to amplify much larger frequencies. Are there solutions for that? Yes, there are solutions for that. The third is scale the Shannon limit. How do we dare scale the Shannon limit? It is like cheating here. What you do is, instead of using only polarization multiplexing, you use space multiplexing, which means instead of one core, in the same cladding, you put more number of cores. In the same core, you put more number of modes. So essentially, you increase the number of lanes in your highway. That is effectively scaling the capacity of the channel. And the fourth is, the noise is a problem. So tackle the noise degradation using some photonic processing. So these are the four approaches on how to scale the capacity. So first example I'll give you for smart choices for pulse shaping. So this is done by Bell Labs. So this is an example of how, this is probably, you can count probably 64 QAM modulation, right? So the probability that your bit stream falls in any of these constellation is the same, because you're just taking sequential bits and you're converting them into a symbol. The probability that you will find a symbol is the same. I mean, the probability of finding this symbol is the same as the probability of finding this symbol, right? Because you have not done anything specific here, right? And this is the same picture as I showed earlier. But this is called as uniform constellation shaping. And this uniform constellation shaping theoretically also has about 1.53 dB gap to channel capacity. People are trying to close this 1.5 dB gap. So that desperate we are. So what we do is, this came from Bell Labs, the idea of what is called as geometric shaping. So instead of using a square constellation, use a circular constellation. That's because here you will, so larger, you don't really have to use equidistant rings. What's the benefit of doing larger separation here? You will have, in each of these rings, you will have different SNRs. Now, when you have different SNRs, you will start kind of beating the Shannon capacity or getting closer to the Shannon capacity. The other method is probabilistic shaping. You see, it's the edges where you will always have a problem. So you populate the center of the constellation with more probability than the outer parts of the constellation, because higher the power, larger is the nonlinearity. So you don't want to populate something at this part, you populate something here. So non-uniform probability distribution. And these are some examples from recent demonstrations, recent as in from 2020, from Infinera and Sienna and Nokia or Acacia. All of them have demonstrated 800 gig, 1.2 terabits per second, but all of them are either using probabilistic shaping or they are using the geometric shaping, right? So this is something that the industry is following now. The second option I told you is space division multiplexing. So instead of using one core, you can use multiple cores. You can use a single core with more number of modes in the system. The reason for increasing the core size is that you can beat the nonlinear limits. You see, you can in a regular Shannon linear system, Shannon limit actually gives you this line. But in a fiber, what happens is, as you try to increase the signal power, the nonlinearity kicks in. So as you increase the signal to noise ratio, the Shannon limit actually, the limit drops down. This is called as a this is popularly called as nonlinear Shannon limit, even though Shannon did not dream about it. But this is a limitation. So it's not about increase in SNR. You should also push the nonlinear threshold in the fiber. Why is a fiber nonlinear? Because it's a very, very small dimension in which a large or a moderate power is confined. So the intensity becomes high. When the intensity becomes high, the material starts responding in a nonlinear fashion. So anyway, this is an example that we did in our lab where we have a 1 kilometer few mode fiber where independent transmitters are used for populating each mode, and through a lantern, what is called as a lantern, and then you have a signal processing happening. So we managed to demonstrate with a lot of signal processing, 2 modes, 21 gigabaud, 4 bits per second. The current record, ECOC 2020, 2021, there was not much on this area, but probably the best until today. Where, this is a fiber manufacturer, Precision. They made the few mode fiber which could support 15 modes, graded index 23 kilometers. Nokia did all the signal processing, 64 QAM, 382 wavelengths. Experiment was, I think, done in NICT. They demonstrated 1 terabit per second. So they've kind of gone beyond, way beyond terabits per second. This is another demonstration. The third approach, as I said, is, this is the attenuation of the fiber. The red line shows the C band where the EDFA is amplifying. But look, there is a lot of space available where the attenuation is low. So use ultra wideband communication. So there's a lot of work going on semiconductor optical amplifiers, using semiconductor optical amplifiers or Raman amplifiers to actually get wideband amplification. So this is an example where C band and L band with probabilistic shaped PDM64 QAM with bit rate of, it's essentially the spectral efficiency is 7.3. This is an example where, again, Nokia with Kylia, which did this semiconductor, basically they demonstrated that you can, SOAs were known to be bad because of the noise, but people don't care about that anymore because their amplification capability becomes much larger than EDFA. This is again an example where SOA was used, where now you can mix all these ideas together. You can use few mode fibers, you can use SOAs, you can use multi-core fibers, put everything together, and that becomes your futuristic communication system. So here is where I stop now. These are the areas where the optical communication group at IIT Madras is working on. The channel could be fiber, free space, or underwater. We do work on coherent communication, signal processing. The coherent, we keep saying coherent communication, but what it turns out is that the phase noise of the laser sources should be really, really low. So we are using our understanding of physics to kind of build laser sources or do some small fixes to the existing laser sources to reduce its line width. The other area I did not talk about is radio over fiber, microwave photonics, where it's completely in the analog domain. There's a colleague of ours who's working on secure communication, quantum communication, and so on. Turns out that quantum key distribution works very well in a specific format if it is done with coherent communication. So I myself am working on something called as secure quantum communication without using single photon sources and without using single photon detectors with the classical coherent test bed. There's also this area which I talked about. I said this, you can do photonic processing for noise reduction and so on. These are, for example, can I have an amplifier which does not add noise so that my problem of SNR degradation is gone? And yes, you can use what are called as phase sensitive amplifiers or parametric amplifiers to do that. So that's something, again, that we are working on. Thank you. I will now stop talking and start listening.
Yeah, ma'am.
Hello. Couple of questions here. Multiple fiber, is it difficult? So I could say it was difficult maybe 5 years ago, but these days, nice fan in, fan out devices are available. Even multi-core amplifiers are available. So it's just that the type of the fiber has to change. So it's not very interesting. It's not, commercial deployers will not be very excited with that idea because they have to change the fiber. But any greenfield demonstrations, this is very, very attractive, looks very attractive. Potential applications of space division in optical communication, again, to increase the spectral efficiency. There's a huge renewal of research in the space division multiplexing in terms of the funding that has gone in the EPSRC or even in the DARPA on using space division multiplexing, re-exploring space division multiplexing, even though it requires a lot more signal processing. Even using multimode fibers itself for slightly longer distance. Multimode fibers are usually used for short distances. There are these nice spatial, what are called as spatial mapping techniques, which you can basically use your implement your neural networks in the optical domain using a series of couplers, and then use these neural networks to demultiplex data. All such nice ideas are coming up. Yeah, thank you for saying that. Biomedical engineering students, opportunities of biophotonics research and job opportunities. I think Dr. Nair should answer that. I am not an expert in that area. Is there an effect of length of communication in the bitrate length product using QPSK? So essentially the length is only determined by, it's not really dependent on the length, but it is dependent on the SNR. So the question you have to ask yourself is there an SNR limitation? So answer is yes. If it is QPSK, your spectral efficiency has gone up, so the SNR requirement will go up. If you go 16 QAM, the spectral efficiency further goes up, SNR requirement further goes up. So it's always a trade-off. You have to really see how much SNR is available to you, how much can you spare, what is the distance that, because basically distance means signal to noise ratio. What are the methods used for generating optical frequency comb? Very, very interesting question. So commercially, resonator based forms. So it's all packaged in a semiconductor resonator based forms. You could also use, what I'm, of course, these commercial transponders, they don't reveal how they do it. But what I'm told is that one way is just hard modulate a semiconductor laser diode, a DFB laser diode. You hard drive that with an RF, you get your frequency comb. And then you take it through a arrayed waveguide grating kind of a filter to clean it up. What we do in the lab is take cascaded phase modulators, intensity modulator followed by phase modulator, adjust the bias in such a way that in a phase modulator, you can always adjust, you can always find out the sweet spot of your bias in such a way that all these Bessel functions, which are representing the amplitudes of the sidebands, they are always, you can, in fact, even you can analytically find out what is that bias voltage which can give you equal lines in all these frequencies. That's what we do in the lab. Laser-based applications in biomedical, biomedical laser are very inseparable. I can tell you that we are in the laser area, at least I'm personally working in developing lasers for 2 micron wavelengths, specifically not for biomedical applications. It is interesting for biomedical applications for kidney stone ablations and so on, but for a different purpose, reducing or generating narrow line lasers for gravitational wave observatory. That is what we are working on. At least my group is interested in the lasers. Do I stop share? I will also put this up for, if there is permission, I would also like to wear the IEEE hat for 2 minutes if we have time.
Yes, ma'am.
Yes, ma'am. Just let me. Okay, I'll just share my screen again. Here is where I actually need your, can you see my screen?
Yes.
Presentation?
Yes.
In just 2 minutes, as we have from the Women in Photonics division of IEEE, we have initiated something called as back to career or research. What we are trying to do is to attempt to fill or seal the leaky pipeline. What I mean by leaky pipeline is this. This is a data from All India Survey of Higher Education. The enrollments in science, technology, engineering, mathematics, essentially STEM, is 43%. 43% of women are enrolling in these programs. 9% in science and engineering, and 14% of scientists and engineers in R&D institutions are women, which means we are training a lot of people, but they are not really getting back into the system and possibly contributing effectively. This is something in the US, and the reasons are very, very intuitive. Everybody understands this. There are these stereotypes: work-life balance, time flexibility, childcare, etc., etc., etc. In a recent survey, people said that, I mean, this is about, the negative outcomes in the career attributed to the fact that they're being women, right? This is a survey result. Let's not get into these details. So we have set up something called as Women in Photonics Task Force. Of course, this is not limited to women. Please feel free to join this task force. There are three-pronged again approach. One is the STEM outreach group. Then we have one group coming from the globalization and chapters, and the third group from professional and strategic development. These are the three verticals under which we need to look at. We are focusing on three different areas. One is what is called as back to career. So here, this is a focused program for those women who have discontinued their career or studies or research. Somebody would have finished a PhD, but is kind of taken a break and is trying to come back to the system. Somebody has been working in that area, has taken a break for whatever reason, right? So this is like a launch pad for, IEEE will be a launch pad for those women who would like to come back to either research or to their career. And what we provide is specific skill trainings, some mentorship, resume, CV assistance, connections to internships. There are several faculty members and industry representatives who have signed up and promised that they will provide internship opportunities to those women who basically want to get back to research. So this is for, again, your own information and publicity. The second thing is the focus area is in the mentorship, the role model growth. So if you ask, if you ask a child as to close your eyes, or you ask any student, ask yourself, close your eyes and imagine a scientist. Is that a man coming in front of you, somebody like an Einstein, or is it a woman coming around? We want more and more people to imagine a woman scientist, right? Only then girls will aspire to become and dare to kind of take up the career. I don't think it is more challenging than any other career path, but somehow there is this fear. So we would like to create more and more role models through different methods. And then the next thing we want to do is to introduce a girl to photonics. So we would like, it's really not introduce a girl to photonics, but introduce children to photonics, let's put this way, right? This is for supporting online as well as offline content creation, which can be taken to schools and things like that. So I stop at this slide by saying that we request volunteers for this. So please do sign up whenever you see some call for volunteers who can reach out to your own local areas, identify what is specific, which will work for your community, your area, and then we will see how this can be integrated. And believe me, there's a lot of funding that is possible, provided we do something very meaningful. So 2022 beginning, we are launching this back to career research. So if you know of someone, or please publicize this program, if you know of someone who will benefit out of it, we'll be happy to help. And of course, in those areas.
How to apply for this program, ma'am? This back to career?
Sorry.
How to apply for this program?
We already had twice sent out forms through IEEE email addresses through that mailing service, and there were several volunteers who had signed up. But we will send, so if you're an IEEE Photonic Society member, it should reach you. So we will do one more round of call for volunteers. So please apply at that time. To apply for back to career as a somebody who would want to come back to career, we are circulating the intake forms in the first week of January. So it will be available. See, there's no point in putting it in Photonic Society website because nobody's coming and seeing that. So we would like to actually circulate it to all the members who can circulate it to the people who are known. The other thing we are trying to do is we are trying to look at people who have gone out of Photonic Society membership in the last 3 years, trying to approach them and trying to see if they want to come back. The program is getting launched in the first week of January. I mean, it's officially launched, but the intake forms are being circulated there. Okay, any other questions?
Since there are no more questions, I think we can wind up, ma'am.
Yeah, sure.
And thank you, ma'am, for giving us such an enriching and information talk on such an interesting topic. Thank you for introducing us to initiatives like the ones you showed, Back to Career program. It was really inspiring to hear about the projects you were working on, and we are honored to have had you here as a speaker for the night. Thank you, ma'am, for joining us.
Thank you.
And thank you, ma'am. And I would like to thank each and everyone who gathered here and actively engaged in the talk and asked questions and made the session an interesting and lively one. Thank you all.
Thank you.
Thank you, madam. Thank you.
Yeah.
Thank you.